Walkthrough should introduce you to the concept of significant figures, why they're important in class, why we use them in physics, and kind of what denotes a significant figure. So first off, why do we learn it? Well, it allows for control of our experimental values, kind of our answers of what we get based on limits of measured information. So why is that? Well, one reason, you can't measure the mass of a book to the nearest nanogram with a triple beam balance. The resolution doesn't go down that low. Same thing for the volume of Slurpee. If you want to measure to the nearest microliter, well, you can't do that with a 1-cup measure. And you can't measure the time it takes to run a lap to the nearest femtosecond with a hand timer. All these things limit what your answer can be, but we get into the habit when we're younger of just writing down everything on the calculator. So you might write down something like, oh, well, it took me 6.2478661 seconds to do something, but that's because that's what my calculator said when I did all the math, because nothing came out cleanly. But you have no way of being able to document that and know that that's kind of the limit of the information you have to work with. So we're going to talk about significant figures to try and make sure we don't get carried away with some of those measurements. So the first rule for whether or not something is significant is that all non-zero numbers are significant. Each example below here shows that there are 4 significant figures. So you can see in the first one, 1, 3, 4, 5, 2, 4, 6, 5, 2, 3, 5, 5, 4, 1, 2, 3. All of those are non-zero numbers, so each of these has 4 significant figures. Second rule is that sandwich zeros are significant. Sandwich zero is just a zero in between 2 non-zero numbers. So here, for example, we have 2003. Those 2 zeros are significant. They are important. They are significant to our measurement because of that 3 on the end. 3405, same deal. 100.3 and 4042. All of those are working off that same basis of those zeros being sandwiched between non-zero numbers, so they are significant to our value. The third rule is the decimal rule. So numbers that are equal to or greater than 1 with a decimal point, that decimal makes every number significant. So for example, 1.000 has only one non-zero number, but because there's that decimal point there, that means someone actually took the time to make sure this was 1.000, not about 1. It is exactly down to 1.000. Same here with 100.0. This isn't 100. This is 100 with 0 tenths. Someone made sure to be specific about that measurement. They had the resolution. They're able to maintain that level of significance. The fourth rule is that all digits in the coefficient of scientific notation are significant. So for example, here we have 1.00 times 10 to the 4th, which would be 10,000. If you look at 10,000 like this, there's only one non-zero number, but we've indicated here that those first 3 zeros are significant with scientific notation. Same here with 20.030 times 10 to the second. Well, that is 203.0. All 4 digits there are significant. That's one way of writing it. The other way we wrote it before would have been fine as well. And here 4.232 times 10 to the negative third. Let 0, 0 like this, 4, 2, 3, 2. Again, here we only have 4 significant figures. We'll talk about why that is in a second, with why the zeros in front aren't significant in a second. So there's our rules for why things are significant. Now the rules for why things aren't significant. So here, for example, first rule is that trailing zeros without a decimal point are not significant. So each of these only has 2 significant figures. This is 240. This is 35,000, 4,200. Only those first digits, 2 digits, are significant. These are not significant figures. Why is that? Well, basically it's because somebody's rounded. They said this is about 240. If they wanted that to be 3 significant figures, they would have put a decimal point at the end, but they didn't. They didn't have the resolution to go down that low. So instead they did, oh, it's about 240. Here it's about 35,000. It's not 34,976, which may have had better equipment they could have measured. So it's about 35,000 based on the limits of what they're measuring or using to do the measurement. So any of these trailing zeros are always going to be non-significant figures. The other category is placeholder zeros, which are kind of leading zeros as opposed to trailing zeros. So we have a decimal that has a 0 in front, okay, when it's less than 1, all of these zeros in front are just holding places. They're pushing the significant figures back, and the only significant figures are the 2 at the very end. And you can see here that 0 is significant there because, well, it is meant to be there. Somebody had the resolution to say that this is, 20 10,000ths as opposed to just 20 100,000ths as opposed to just 2 10,000ths. Okay. Now, what does this mean for when we do math? Well, here's a quick summary of all the rules again. Non-zero numbers are significant, same with zeros are significant. Decimal rule, intent to put decimal point in there, basically everything is significant as long as the number is greater than 1. All the digits in the coefficient scientific notation are significant. Non-significant numbers, again, trailing zeros without that decimal point are non-significant. Placeholder zeros with a number less than 1 are also non-significant. Now we put that into math, and here's what happens because of it. We want to limit our answers to the same number of significant figures as your least significant piece of information given. So what does that mean? What does it look like in practice? Well, quick examples here. We have 15 times 3. Well, we all know 15 times 3 is 45. However, if we go off our significant figure rule, 3 only has one significant figure. 15 has 2. 45 also has 2. But I am limited to that one significant figure from the number 3. So I need to round my number, 45, to one significant figure. If I round 45 to one significant figure, that means 15 times 3 is actually 50. That 5 is going to cause the 4 to round up. However, 15 times 3.0 is also 45. 3.0 has two significant figures. 15 has two significant figures. So my answer gets two significant figures, so it stays at 45. 15 times 3.00, well, we know that's 45, but so we have two significant figures there. Here we have 3, here we have 2, so that means we have the right answer again, because now instead of the 3 being limiting, it's the 15 that is limiting my answer. If instead it was 15.0 times 3.00, well, that's when you would make it 45.0, because both these two have 3 significant figures. So my answer would need that 3 significant figures. So hopefully this makes sense, and hopefully some of the practice problems associated with this helped you out.